Hey everyone, and welcome. I am absolutely thrilled to have you here today. If you're joining us, it means you're a focused learner who loves to cut through the noise and get straight to the why and the how of complex topics. Today, we're cracking the code on what is arguably one of the most powerful mathematical tools out there, logarithms. Seriously, these things are the hidden secret behind how we measure the devastating power of earthquakes, or how epidemiologists track the rapid spread of viral outbreaks. We are going to completely demystify them, break them down visually, and show you exactly how they work. You aren't just going to memorize formulas today, you're going to actually understand the beautiful underlying logic behind them. Let's get started!
Okay, let's dive into this. Here is our roadmap for the explainer today. We'll start with Section 1, the rules of logarithms. Then, Section 2 covers core operational shortcuts. In Section 3, we'll dive into exploring natural logarithms. Section 4 is all about visualizing exponential symmetry. And finally, Section 5, transforming to linear forms.
Kicking things off with Section 1, the rules of logarithms, understanding the foundational grammar.
So what exactly is a logarithm? Well, it's quite simply the direct inverse of an exponent. It's basically a way of asking a specific mathematical question backwards. If we have the equation y equals a to the power of x, the logarithm translates that exact same relationship into x equals the log base a of y. Let's ground this with a quick mental math word problem. Imagine you have a bacteria population doubling over time. If 2 to the power of 3 equals 8, the logarithm just turns around and asks, hey, to what power do we need to raise our base of 2 to end up with 8? And the answer, of course, is 3. The logarithm just takes the base and the end result and isolates the power required to get there. It perfectly flips the script on exponents.
Now, what's really interesting about this is how the logic just perfectly clicks into place when you juxtapose these two basic identities. First, look at log base a of a equals 1. Why is that? Just ask yourself, to what power do I need to raise a base to get that exact same number back? Exactly 1. For instance, log base 10 of 10 is simply 1. On the flip side, we have log base a of 1 equals 0. Think about it. To what power do I need to raise any base to get a result of 1? 0, because any non-zero base raised to the power of 0 is always 1. So log base 10 of 1 is exactly 0. These aren't just random rules, they're logical certainties based entirely on how exponentials actually work.
And building directly on that logic, we get these amazing cancellation properties. The first equation here shows log base a of a to the power of x equals x. If you take a base a, raise it to the power of x, and then immediately turn around and ask, hey, what power do I raise a to get this exact value? Well, obviously the answer is just x. The exponent and the logarithm perfectly undo one another. It's literally like walking 3 steps forward and then taking 3 steps right back. You end up exactly where you started. And as you can see in the second equation, it works the other way too. A raised to the power of log base a of x is just x. They act as a conceptual lock and key.
Moving right along to Section 2, core operational shortcuts, simplifying complex math.
This table right here, this is the absolute heart of why logarithms were historically so revolutionary. In fact, before we had computers or calculators, sailors and astronomers used these exact rules to simplify massive navigational calculations to cross the seas. Look at the product rule. It shows that log base a of x times y equals log base a of x plus log base a of y. A super complicated multiplication problem is instantly downgraded into simple addition. The division rule does the same thing, turning x divided by y into straightforward subtraction. But the power rule, that one is truly magical. Log base a of x to the power of m equals m times log base a of x. Let's frame that as a practical problem. Imagine calculating the log of 100 to the 5th power. Instead of dealing with some monstrous number, that huge exponent of 5 just drops right down to the front. Boom, it becomes 5 times the log of 100. Logarithms literally compress the scale of mathematics.
And that brings us to a really brilliant illustration of the power rule in action. We have a special case. Log base a of the fraction 1 divided by x equals negative log base a of x. Now why does this happen? Well, in the language of exponents, 1 over x is the exact same thing as x to the power of negative 1. And according to that power rule we just looked at, that negative 1 exponent just drops right down to the front of the logarithm. It perfectly demonstrates how fractions and negative logarithms are mathematically identical concepts. Pretty cool, right?
Let's move to Section 3 and see how this builds. Exploring natural logarithms, the special dialect of base e.
So, you might hear the phrase natural logarithm and wonder what makes it natural. Simply put, it's just a logarithm that uses the base of e. Now, e is a famous mathematical constant, roughly equal to 2.718. But why does it matter? Well, think about a real-world problem. If you're calculating continuous compound interest in a bank account, e literally represents the mathematical speed limit of that financial growth. Because it's so ubiquitous in nature and finance, we give log base e its own shorthand notation, lnx. So whenever you see lnx, just know it silently means log base e of x. But here's the absolute most important takeaway. Don't panic when you see ln. Every single standard logarithm rule we just went over applies perfectly to natural logarithms. The grammar hasn't changed at all. We're just using a highly specific vocabulary word.
And just to prove that point, look at this. If y equals e to the power of x, then x equals the natural log of y. This is a direct one-to-one parallel with our foundational definition from earlier. The inverse relationship holds absolutely true. The natural log is just a perfect tool for undoing an exponential function when the base happens to be e.
All right, let's shift gears to section 4, visualizing exponential symmetry, seeing the math.
I absolutely love looking at this visually because it brilliantly illustrates the concept of mathematical inverses. Notice that dashed black line shooting perfectly diagonally through the origin? That is the line y equals x. Now look at the blue dashed curve rocketing upwards. That's our exponential function, y equals e to the power of x. It crosses the vertical y-axis right at 1. Then look at the solid red curve, gracefully arching out to the right. That is our natural logarithm, y equals ln x, and it crosses the horizontal x-axis right at 1. Do you see it? The blue curve and the red curve are perfect geometric mirror images of one another, reflected exactly across that diagonal line. Because the equations undo each other perfectly, their graphs are perfectly mirrored reflections. It is just so elegant.
Finally, let's hit section 5, transforming to linear forms, the power of straightening curves.
So, the crucial point is this. In the real world, data rarely behaves nicely. Relationships usually take the form of incredibly complex curves, like y equals k times x to the power of n, or y equals k times a to the power of x. And let's be honest, those curves are notoriously difficult to analyze. But if you apply logarithmic rules to both sides of those equations, you can separate multiplied constants, pull down those tricky exponents, and physically convert those messy curves into the absolute gold standard of simple data analysis, the straight line equation, y equals mx plus c. Let's put this into a practical scenario. Imagine you're tracking a rapidly multiplying bacteria culture in a lab. It forms this massive, unreadable exponential curve. By applying logarithms, you literally flatten that steep curve into a straight line. That allows you to easily predict exactly how many bacteria will exist next week using basic linear algebra. Logarithms act as mathematical straighteners. It's a total game changer for working with real-world data.
Which leaves us with this final thought. We have seen how logarithms compress massive operations, how they completely undo exponential growth, and how they literally flattened curved data into perfectly straight lines. They are, without a doubt, the decoder ring for exponential behavior. So, if logarithms can straighten the complex curves of mathematics, what hidden linear patterns could they help you uncover in the complex, messy data of the real world? Thank you so much for exploring this with me today. Keep analyzing, keep learning, and I will see you on the next explainer.